Diploma in Physics and did his PhD in Weimar at the Hochschule for Architecture. He has more than 13 years experience with SEM/TM, and he worked at the Otto Schott Institute for Glass Chemistry at the University of Jena. In 2010 he retired, but he still cannot stop working. During climbing on the mountains, he is still at the institute and did glass chemistry, and he used, since his 13 years of experience, SEM/TM to characterize all sorts of glass. And we are looking forward to your presentation.
Thank you for the introduction. I will talk a little bit about glasses, a few words about glasses. So we are dealing only with inorganic glasses, nothing about organic glasses. It's a completely different field. Say something about what do we investigate with microanalytic techniques. And these are things we have: liquid immiscibility. Usually we had investigated glasses prepared in our institute, so our chemists had the idea what they mixed together and melted. So usually they could tell me what is in these samples, and the problem was the distribution of the elements. A large field is the crystallization of glasses. A few words about the instrumentation, and then the examples. And glasses are a group of materials which are very sensitive against radiation. So there are many possibilities to make mistakes during analysis and about radiation damage. A lot of things have been said in the morning, so some positions I can shorten my talk, just to demonstrate for those who are not so familiar with glasses. An example for inorganic or silicate glass: if you have silicon dioxide in a crystallized form, then you have linked SiO4 tetrahedra in a very regular shape. They form 6 rings. This is a planar view, and this is the crystalline form. And when this regular shape is changed to an irregular shape form, then you will get the amorphous SiO2, also such SiO4 tetrahedra, sometimes also such 6 rings, but very different. And this then will be a glass. If you look for the temperature dependence of special properties, for instance, here the specific heat for the crystal and for the glass phase, then you will a sharp step for the crystal, and continuously changing for the glass. And in case of the crystal, you have a sharp melting point, melting temperature. In case of the glass, you have a transformation region. And this is important when we investigate our glasses in the microscope. Which elements are typical in glass science? So the classical network, such a network can be formed not only from silicon dioxide, can formed, for instance, from boron oxide, phosphorus oxide, tellurium, beryllium fluoride, not only oxides, zirconium fluoride, aluminum fluoride, or very special system, germanium selenide, or antimony oxide. They all can form networks and form glasses. And in these networks, you can introduce other elements as so-called network modifiers. They will modify the structures, and additionally it's possible to add to the melt other components, especially titanium and zirconium, used, for instance, as nuclei for crystallization. And at the end, almost all other elements of the periodic table can be added as dopants. So when you are investigating glasses in material science, then you will meet almost all elements of the periodic table. Some possibilities how it looks like. This is from a natural glass, from an obsidian, crystalline precipitation, which grew when the melt cooled down, and this is such a liquid immiscibility in a phosphate glass. So looks, maybe a glass looks like. The question, why do we use microanalysis? For most of you, glasses are or shall be homogeneous materials and not inhomogeneous materials. We have, in many cases, we have inhomogeneous. For instance, this one is exactly this. It's only silicon dioxide and sodium dioxide, and it's the bonds between the tetrahedra are broken. The large sodium ions are in between the two oxygen ions as bridges, and if you melt this material, cool it down, then it forms such droplets, and that is a typical task for analysis. Another version from an experiment in the past, a lead borate glass forms two different phases during cooling. The heavy lead rich phase and the much lighter boron rich phase. If you give them time enough under terrestrial conditions, then you will have two layers. After a short time of microgravity during a parabolic flight, so it's not time enough to completely separate, and when you melt the same glass in the space, this was done in the space laboratory Mir. After hours of gravity, you have completely homogeneous distributed droplets in a lead-rich droplets in a borate phase, and these are examples for the investigation for the microanalysis, why we need microanalysis. If we cool down a glass and reheat it afterwards, typically in two steps, then it will partially or completely crystallize, and we will get glass ceramic material. For instance, then such crystals will grow. These are microcrystals, and then this material, for instance, will be machinable with different tools. This this material was developed in our institute. For instance, this one, you can use it, for instance, as a bone implant. After operation, and boring a hole in your head. Other examples of crystals which grow in the glass, in the glassy matrix, for instance, these boron-rich silicate glasses, crystals, these lucite crystals, resinite, you will see later on, and apatite crystals. All these are examples for the investigation of glass ceramic materials. And why do we need WDX? So very often we have the elements boron, nitrogen, oxygen, and fluorine. We have a lot of overlaps. All these things are said in the morning. So that's why it's not necessary to talk about more. Optical glasses, usual with non-linear properties, often are doped with different rare earth elements. They have a lot of lines and make a lot of problems. The instruments we used in our institute, this was the old one I found when I started in '75 in the institute. It was a gel microscope with two such vertical spectrometers with curved monochromatic crystals, already shown in the morning. And the intensity which we can, the counts we can, the count rate we can measure is depending on the distance, on the way through the spectrometer. So the other one was the size microscope with the microspec WDX, also with curved crystal focused spectrometer, but not vertically with like the gel. It's tilted. That means when you shift a little bit up and down your sample, so the influence will not so high like in the vertical version. And now, since 2007, we have the gel microscope again, and with a trident, with the parallel beam spectrometer, with the light element version, with the legs, and it looks like this. So this is a view inside the camera. So this is the spectrometer, the head of the spectrometer. And just for interest, measured for these three types of spectrometers, the relative intensity change with changing of the Z position if you move up and down the sample from the exact position. So very similar are these two spectrometers. When you when the deviation is about 25 micrometers, then the count rate will drop down to about 90%. Not so sensitive was the other spectrometer, since it had a different geometry. For our light element spectrometer, we measured, we took the line, measured in the correct position. This is this silicon alpha line too. If the sample is correct positioned in that direction, when we move up the sample, the line will shift and the intensity will drop down to about 80% and shift to lower energies. When we move up this 100 micrometers above the correct position, then the energy shift will go to the other side, and the intensity also goes is lower. So with this, I think this shows that's really important to position this sample at the exact position. Just for completion, the EDX line in the same energy region, so this is much broader, so it's inside this line. Here I wanted to give oh, the computer makes a little bit different signs. I had to use the very old graph because of our exactly at that time when I agreed to give a talk here, then our microscope failed and no water was flowing to the microscope, and it will be repaired next week. So I could not measure the newer one, but this is interesting though. This is a mouse, and so okay. But just to see, even with this really old system, the WDX resolution is high, so it was no problem to separate the K alpha 1 and 2 lines for iron. So again, some classes. The typical shock-resistant glass everyone knows, Jena glass, Pyrex glass, or the glasses with very low thermal expansion coefficient are these. Barium and titanium containing glasses in glass ceramics in our institute investigated for piezoelectric materials. Optical glasses, the so-called biovarit, this was the shell I came around. Material from our institute, and a real special material, this nitrogen oxygen glass ceramic material. Can skip it. Boron plays a very important role in glass. Günter Völksch already in the morning said a lot of things about the measuring of boron. So again, it's no problem to measure boron in such compounds which contain very high amounts of boron. But in the Duran glass, for instance, the shock-resistant glass, the boron content is about 4 weight%, and this makes it complicated. Sometimes it's enough. This was an example. Sometimes it's enough to say, is there much boron or not? This was a glass splinter sent from a milk company to us. They had a customer found a glass splinter in a yogurt cap, and the question was, does it come from the factory or does it come from outside? And so with this low boron peak, we could say it's not from silicate glass. These are typical compositions. It's just from a glass from this region, so it has to be flat glass, so it could not come from the tubes, the glass tubes in the factory, so sometimes this is enough, but better is to make quantitative analysis, and this is possible too. This is from your company, the test class, when I bought the instrument. I could not do it better, so I used your results. You have the glass used to run as standard. I sent a sample for testing, which was prepared in our institute. This was the synthetical composition, the wet chemical analysis in our institute, and in the chemical institute this is the holy value. All other measurements are bad. And this was the measurement from I got from Mr. Völksch, and you see it's for a glass really good analysis. We could not do it better. A very complicated system, oxynitride glass ceramics, prepared in our institute. This was the synthetical composition, two different analyses, and here an example for the problem already mentioned in the morning, the problem of standard and the problem of irradiation damage. This standard is a glass ceramic material, partially crystallized, and this is the glass sample. You see for the WDX measurements, for standard measurements on this area, you will not see any irradiation damage, but here for each element another field was irradiated, and nevertheless you see the damaged surface, but analysis worked quite good. But this in general, the radiation damage makes us a lot of problems. Another example is the Fresnite glass ceramics. It's produced via electrolytical induced crystallization. There's a crucible, a metal crucible with a central wire inside, and between these two a voltage is applied, and then crystallization will start. Far from the wire, you will find these dendritic Fresnite crystals, and near to the wire then you've found such structures, and the question was which phases crystallize there, and we could identify in the region E, this is the dendritic Fresnite, the same like here. This is also Fresnite, and in this region H, there we have glass and a barium silicate without any titanium, and this one can see here in the mappings. Two of them could be done by EDX, and the others we made by WDX. All the lines from the table I marked here. We used these lines, and the conditions which were applied 20 kV voltage, 0.3 nanoamps for the EDX measurements, and 20 nanoamps for the WDX measurements. This is a very interesting material. That's why we did a lot of work with that. Now we go back to the glass I gave you at the beginning. Again, the 15 molar percent sodium oxide, 85 molar percent silicon dioxide. These are the elementary composition. A picture how this structure looks like after cooling the melt. And what did we do? We took the sample, moved the electron beam across this sample, wrote a track over the sample, and then looked what happened. Then a view to the cross section showed us that this is the original surface. The track was in this direction, and in this large region, the structure, this structure was changed. This is the same like this, and here it's much coarser, and additionally a valley is burned into this surface. These are strong conditions, but not so strong, not too strong for WDX. 20 kV, 10 nanoamps, and this is the depth scale here. This measured. The depth scale is 600 angstroms, but the width is more than 10 micrometers, and this was done with a focused beam, not with a defocused beam. But so many things may happen. And when you fix the beam and write and register the sodium K alpha, oh, interesting. It's got sodium K alpha line under these a little bit strong conditions, but to demonstrate I think it's okay. Over the time, then you see after about 10 seconds, you have still 20% of the sodium K alpha intensity. So this is a problem which makes it very, very complicated to measure alkalis in any glasses, and in many cases it does not work. A little bit stronger then you will get these profiles, but this is not, that's usually not done in the microscope. For this track we had here measured across this track the intensity, then you will find an enrichment in silicon and depletion in sodium K alpha. So the sample is completely changed by the electron beam. Everyone knows another example, such a Fresnoide, it's a barium titanium Fresnoide, investigated in the TM, so it can be under the electron beam change from crystal to amorphous material. And another system where a lot of things happen. This is a silicate system with many additional elements inside. It's a commercial glass, and when you use an electron beam of 20 PV, we used currents between 0.01 nanoamps to 600 nanoamps, 15.5 minutes, and the defocused beam irradiated the region 200 micrometers in square. Then, at first, you can observe on the sample optically that you will have a browning of this glass, and you can see the scanned region. You can measure this browning, this is not so important here, but when you then, this glass after electron, after irradiation with electrons, then crystallize, then you will find that in the region with this diameter and this depth, the glass structure is completely changed and will crystallize very different from the surrounding. And when you, this is the optical cross-section beneath this irradiated region. This is after etching the material, the SEM picture in this region, and you can observe that you have a real large area where the crystallization behavior of the material is changed only by the irradiation with electrons before crystallization starts. And very strange, this smaller area in the middle. Nobody knows why this state, this saddle here appeared. But what I want to show is that irradiation with electrons of glasses can completely change the structure of the material and makes analysis quite complicated. So these are the lines we used for analysis of these materials, and they are all lines, they all can measure with the flex spectrometer system. Then that's it.